Okay, I'm going to take that as a no. So let's remind what happened last time. So last time we talked about injectivity and projectivity, and so these are the things I owed you, that free modules are projective and that every projective module is a direct sum end of a free module. So so what we did was, so we introduced the notion of we introduced the notion of projective, and that projective modules are ones that take exact sequences to exact sequence in the functor represented by it. And then there was injective modules, right, which took exact sequences to exact sequences in the functor co-represented by it. Okay, and then we found some of the so you would think that that you need to take, for this one you need to take injections to injections and surjections to surjections. And for this one, since everything gets flipped, you want surjections to go to injections and injections to go to surjections. Okay, you think that you need to check two things. It turned out, right, that we had some freebies. Okay, and the freebies were this, right? So that for any module, right, an injection, so the functor represented by M takes injections to injections. So you always get this left exactness, right? Similarly, you always get surjections to injections for the functor that's co-represented. So whatever you do, whenever you take an exact sequence, you get the left part for free. Okay, so you get the left part of the sequence for free. All right, and that's just from general properties of limits and colimits that we discussed last semester. Okay, so all right, so let's go back to what we're doing today. So I want to talk about the things that I owe you. And so let me just as a reminder again, right? So P is projective, right? If and only if morphisms, or so the functor applied to the functor represented by P applied to surjections is a surjection, right? And Q is an injective R module. If and only if, well, the functor co-represented by P takes injections to surjections. Okay, so this was the notation that we talked about last time, and it makes sense to apply the functor to morphisms. So this is, I think Liam was asking about that when we talked about this. And the freebies were that both of them are always like left exact. So the thing that you get in the end is going to be a left exact sequence. Okay, so let's talk about another formulation of these two criteria. Okay, so okay, so what we're going to do is well, let's make this a topic here. Okay, and I guess I'm going to do it for injectivity too, but so let P be a projective R module. Okay, so what this means is that given a surjection, right? So this means that when we're given a surjection here, so this is a surjective map of R modules. Right, then this means that this thing here, so what we can do is we just apply the functor to it. We apply the functor represented by P, okay? And we get another map. So this is HP of V maps to HP. So this is HP of F. Let's call this F here. Okay, and this goes to HP of V prime prime. Okay, and then we can kind of spell out what these are. So this thing, again, this is just another notation for this functor. This is this functor again. Okay, and this is, we called this thing F lower star too. And what it does is it takes a morphism here, right, and it maps it to the morphism here, right, where you just compose these two. Okay, so this is really you know, this this is the F star of phi. Okay, so this is what we had, and that this is, when this is a surjection, this is a surjection. Okay, so yeah, so the idea is that if F is surjective, then F lower star is surjective. Okay, so let's look at this in terms of diagrams, right? Diagrams, right? Okay, so what we'll have is we're given, okay, so what does the push forward map do, right? So given, so we're given this situation. All right, so this is what we're given, P, so this is phi, and then we have F here. So I'm just writing this map over. So what I'm writing here is I'm drawing this again. I'm drawing this map, okay? Okay, so this is what we're given, right? And then this F lower star is the arrow that you get when you fill this in, right? Nope, that's the wrong way. Okay, so this is the output, right? So all you're doing is completing this triangle, okay, by using the composition. This is the composition of the two maps, okay? The surjectivity condition, okay, the surjectivity condition looks like this, okay? It says that it's the other way. It's that, okay, if we have a situation like this, where I have a map here, psi, we're given this map F, okay? So this is what we're given. So anytime I have one of these, all right, for projective modules, right, we get the following, right? We get that there exists this map. So maybe write this as a dotted arrow, right, that fills in the diagram. There's phi here, there's F here, right? So this is the psi that we're given, and then there exists some phi that fills this in. Psi is equal to F lower star of phi. Okay, so this thing here, so this the fact that you can fill in any map like this, that you can lift the map's psi, right, to a map phi, right, is equivalent to projectivity. So projectivity of P is equivalent to lifting maps psi to maps phi. Okay, so this is one way of formulating this. Okay, it's saying that whenever you have one of the, so how do you determine when a module is projective, and how do you prove it, right? Well, you set up an arbitrary diagram like this, right, from V to V prime, and you have this P, and then the game is that you need to prove that this phi exists, making this diagram commute. Okay, so that's how we show that something is projective.
So okay, phi exists for all.
Yeah, so the quantifier is, the quantifiers are right? So for all psi in mod R, so it's just the quantifiers for surjectivity from P to V prime prime. There exists a phi in mod R P to V such that psi is equal to F lower star phi. Okay, and then the input into this. Okay, you also have so this is the quantifiers here. So every one of these, there's one of these, but also there's the assumption, right? You're assuming that this map here is surjective. Okay, because you need to show that surjections go to surjections. Right. All right, and this is just the quantifier for what it means to be, for this map F lower star to be surjective. And that's what it means in terms of diagrams like this. Okay, so let's do an example. Okay, so let's do a lemma. Okay, every free module is projective. Okay, so let's do the proof of this. Okay, so so let F be a free module. Okay, so what does that mean? So this means that F looks like the direct sum I and I of R's here. Okay, and so so I want to remind you what the direct sum means here. So this is over an index set. So in this thing, only find, so it's like they're big tuples, right? So here, this is a collection of Ri's for I and I, but only finitely many Ri's are non-zero. Okay, that's the difference between the direct sum and the direct product. Okay. Okay, so let this be a free R module. Okay, then and so what we're going to do is we'll let let this collection EI for I and I be a basis. Okay, so these are like the standard basis vectors in this like infinite dimensional. It's like an infinite dimensional vector space, but you know, just copies of R. Okay, so let this be a basis. Okay, and so what we're going to do is we're going to set up our diagram. So suppose we have a diagram as in the criteria. Suppose that you know, we have a surjective map. We have this. So here we have a surjective map of R modules in a map psi. Okay, so this is this part here. This is a surjective map of R modules. And then this thing is some given morphism. Okay, so what we need to do is we need to show.
So do we know that psi is surjective?
No, we do not know that psi is surjective. It's just any map in the world.
Okay.
Any map in the world. Okay, so we need to show that this thing exists. And makes the diagram commute. Okay, so that's what we need to do. Okay, so this is pretty easy because we have basis vectors. Okay, so we know, so what we're going to do is we're just going to look at the image of the basis vectors. Okay, here we're going to look at the image of these guys, and then they're going to go to something here. But because the map is surjective, right, we can find guys in the V that map to the things that the basis vectors map to. And that's what's going to allow us to define the map, the vertical green map. Okay, so let me write that down. Okay, so psi EI is equal to VI prime prime in V prime prime for that's the definition. VI prime. Well, okay, so this is the name. I'm just going to give these things a name. Okay, so by surjectivity, and I guess technically the axiom of choice, right? So there exists some VI in V such that, I mean, I guess this exists, but making a choice is what we're going to do. Okay, so there exist some things like this. And so what we're going to do is we're going to let this collection of VI for I and I be such a choice. Maybe I should make this more like a sequence. Be such a choice. Okay, so there exists some things in so this map's surjective. So what we're doing is we're just picking pre-images out. Okay, and so what we'll do is we define F to V here to be the map of R modules determined by, okay, then we just do phi of EI, and this is going to be VI, like so. Right, and that's it. That's all you do. That was Alexa. Sorry. No, start. Look, I can unplug it. Okay. Okay, so that's all we do. So we just pick, some pre-images, and then we make a map this way. Okay, and since we showed that this green map exists, right? The green map here. So what's our green map at the end of the day? Well, this is how the green map is defined. Okay. Yeah, since we showed that exists, that proves that F is free. Okay, so are there any questions on this? So the axiom of choice part, maybe, is that if you have a collection of sets indexed by some other set I, the fact that there exists a choice function that you can pick a single element out of each of those sets, and the sets here are, say, the pre-images of V prime prime, right? The fact that there exists a choice function is exactly the axiom of choice. Okay. All right. So we proved that every projective module is free. So there was the other thing that I owed you, which was that that every every projective module was a direct summand of a free module. So there's something stronger, right? There's yeah, it says that every free module is projective, but not only that, every projective module will look like a direct summand of a free module. Okay, and in order to prove that, I need to talk about splittings. Okay, so let's talk about splittings for a second. So this is something we need to prove that statement about projective modules. Okay, so what we're going to do is we're going to take we're going to take an exact sequence of R modules. So let this be an exact sequence of R modules. Okay, and let's call this thing star. All right. So let me give you a definition of what splittings are. Okay, so a left splitting So a left splitting of star is a map, and it's going to be a map tau from M to M prime, such that J composed with tau is the identity on M prime. Okay, and then here's the picture, right? So we'll have our sequence here. And then this is J, and this is P. This is the injective map. This is the projective map, right? And then we're going to have this map tau here. And so if you go J, then tau, sorry, this should be the other way. J, then tau. So tau, J. So if you go J, then tau, then you're gonna get the identity. Okay. So a right splitting is something that's going to be very similar. So a right splitting right is a map here sigma M prime prime to M such that so it's going to be the same thing. So what you're going to do is you're going to take sigma, and then you're going to apply P, and then this is going to be the identity on M prime prime. Okay, so here we'll write it out again. So you go like this, M prime, M prime prime, and then we're going to go back like this, sigma, 0. Okay, such that this holds. Okay, so okay, so here's P and J. Okay, so yeah, so this is a right splitting. Okay, and we'll say that okay, so this is what we'll do. So let me give another definition. This is just kind of the so okay, so we say a sequence star is left split if it has a left splitting. Okay. Similarly, we say a sequence is right split star here is right split if it has a right splitting. So we're saying that there exists. So the difference is the quantifiers, right? So a left splitting is a choice. So you fix a choice, and this is just saying that one such thing exists. Sometimes one thing that you like to study is the collection of all splittings. So that becomes an important thing. That's actually something that I'm looking at right now. So one of my research projects is one of the things I need to study is the set of splittings of a certain sequence. Okay. All right, so let me give you the theorem. The theorem says that these things are all equivalent. Okay, so theorem. I can't erase that for some reason. So theorem. So consider an exact sequence. An exact sequence of R modules. So here we go 0 to M prime to M prime prime to 0, and we'll call this thing star. Okay, and we'll call this J, and we'll call this P. All right. So the following are equivalent. Okay. What are the equivalent things? 1, M is isomorphic to M prime direct sum M prime prime with J and P being equivalent to the standard injections and projections. Let's say the standard inclusion and projection. 2, this sequence star is left split. Okay. And 3, star is right split. Okay, and if any of these things happens, we just say that the sequence is split. Okay, so yeah, so if this thing is really like a direct sum, and this is the projection onto this, and this is the projection onto M prime prime, and this is the inclusion of M prime into here, that's the same thing as being a left split or right split, having these sections.
If being left split and right split are equivalent, why are there two different notions?
Yeah, so let me give you a definition. Because we need to prove it, right? If any of these equivalent conditions holds, we call the sequence split. Okay, so we say it's a split exact sequence. Okay, and yeah, we don't. This is like a one. So left split and one right split are like a one-time thing. I'm going to tell you about this once, for the rest of your life, and then when people say split, they'll mean any one of these 3 equivalent conditions. Okay, so let's do the proof of the theorem. Okay, so here's the proof. So the first one is easy. So 1 implies 2 and 3. So okay, so 1. Okay, so this part is this is straightforward. Right? So if, M is M prime direct sum M prime prime, right? And that's so it has both. So let's put it like this. So this thing has both injections and projections. And projections for M prime and M prime prime. Okay, so yeah, so making the exact sequence out of this direct sum is easy. So making the left splittings and right splittings, right? So if you include M, right, you can if you include M prime, you can just project back down, right? Okay. Same thing goes with M. If you project, you can also just include it back. Okay, so let's do 2 implies 1. Okay, so suppose that we have some left splitting. Suppose that we have some left splitting tau. Okay, so here we have 0 goes to M prime, goes to M, goes to M prime prime, and this goes to 0, and then we have this thing tau, right, where if I include J and then I go back to tau, that we have the identity. Okay. Okay, so what we're going to do is we need to show that there's a map, right? We need to show that there's a map. So we construct a map. So we'll construct a map here. Okay, so let's just write down the map. Here we're going to do M to M prime direct sum, M prime prime. This is going to be phi. And here we take M, and it goes to tau M P of M. Okay, so this is our map. And so we claim that this is an isomorphism. Okay. So, and so let me just write down a little observation here, right? Is that really you can write down an element of M, right? This M as kind of like a combination of two things. So this might be familiar from linear algebra if you've ever had like a projection operator, right? And so let me just make like a little observation here. Okay, so this is a good way to think about it, is that M is really M minus, and then we'll do J tau of M, okay, plus J tau of M. So I added and I subtracted the same thing, okay? And so what's going to happen is that this thing is like the M prime prime part, and then this part here is the M prime part. And I find this useful. And you do the exact same, you can do the exact same thing if you have a splitting on the other side. Okay? But this is this is how you decompose it. Okay, but let's just go back to this proof. Let's go back to this proof here. Okay, so let's show injectivity of this map phi. Okay, so injectivity. So we need to show that it's injective and that it's surjective. Okay, so suppose that phi of M1 is equal to phi of M2. Okay, at the end of the day, to show that it's injective, we need to show that M1 is equal to M2. All right. Okay, so this is the case, right? If and only if, well, it's in two components, so the two components need to be equal. And P of M1 is equal to P of M2. Okay, so if we have that these two things are equal, it has two components, so the two components must be equal. Where did I write down the map? Did I write down the map? Oh yeah, here's the map. Right. So we're writing down this map. It has two components, right? And so we're just equating the two components. Okay. And so I guess I'll need to label this. So let's call this dagger. Okay. So let's work on the first thing. Okay. So if P of M1 is equal to P of M2, right? This is the same thing as, okay, so what we'll do is we get to subtract them and we get to use linearity. Maybe I can put an if and only if M1 minus M2 is equal to 0. Okay, and so this tells us that M1 minus M2 is in the kernel of the map P. Okay, but by exactness, so the sequence was exact of, what did I call this sequence? Did I give the sequence star name? Star. Okay, so by exactness of star, okay, so we know there exists some M3 in M prime such that, well, M1 minus M2 is J of M3. Okay, because that's what the kernel of the map is. The kernel is the image of the previous map. That's what it means to be an exact sequence. So let's apply tau to both sides, right? to both sides of this equation. Okay, so tau is a linear map. So we get tau of M1 minus tau of M2 is equal to tau of J of M3. Okay, so if I didn't say that before, tau needs to be a map of modules. Okay, that's important. Okay, so this is tau of J of M3, and now we use the property that that this is a section part. So here we're using that this is M3. So this is the uses the left splitting property. Okay. Okay, and then I have that this is 0. Okay, by star. So what did I say? What was star here? Oh yeah. So now we get to so by dagger. All right, so okay, so this is 0 here. So this is by dagger. Okay, so this was the other part. We get to use the other part of the equation here. So here we're using this part here. Right, so we suppose that these two things were equal, which means their tau parts were equal. Okay, so now this shows that M3, so this means that M3 is equal to 0. And so this implies that M1 minus M2, which was J of M3, and this thing is 0. Okay, so M1 is equal to M2. And the map is injective. Okay. All right, so we proved that this map is injective. It remains to show that the map is surjective now. Okay, so let's do surjectivity. All right, surjectivity. Okay, so what we're going to do is, as usual, we're just going to take a random element in the codomain and show that there's something that maps to it. Okay, so we're going to let M prime and M prime prime be in the codomain here. Okay, so let's just kind of use all our properties that we have. Okay, so we can get something that maps to M prime prime. Right, so again, we need to show that there's some M such that phi of M is going to give us this tuple here. Okay, so that's what we're showing. So since P is surjective, right, this implies that there exists some M in M where P of M is equal to M prime prime. Okay, tau is a splitting. Okay, since tau is a splitting, this implies that tau of J of M prime is equal to M prime. Okay, so what we're going to do is we're going to cook up an element using these two properties. And it's going to come back to this original observation here, this thing here. So now we're going to use this observation. Okay, so we're going back down. Okay, so we're going to use the observation. Okay, so what we're going to do is we're going to let M tilde be this thing. We're going to do M minus J of tau of M, M prime. Oh, let's see. I guess I want to do that. Minus J of tau. Let's see what happens. Okay, this is what I wrote down. We'll see if this works. Plus J of M prime. Okay, so that's what I want to happen. Okay, so let's do this, and then we need to check that this works. Okay, well, I guess this isn't quite the observation, but it's the same idea. Okay, so. Okay, so let's check that this works. So P of M tilde is, so P of M tilde is, well, these things are in the kernel here. This is P of, well, M, and then we have just plus stuff in the kernel. Right, which is just P of M, right, which was M prime prime. Okay, and so the stuff in the kernel, right, that's when I'm talking about this stuff. Okay, similarly, tau of M tilde. Okay, so this is, well, we have tau of M minus tau of J of tau of M. Okay, so that's why we wanted to do this, right? Because we're going to get some cancellation here, plus tau of J of M prime. Okay, so now what are we going to use? So we're going to use this splitting property again. The splitting property is that these things cancel, so that's just the identity, right? And then once those cancel, right, we just have that all that's left over is really, well, I shouldn't use pink, brown maybe. Okay, so this thing here, right, this thing is just 0 because it's just tau M minus tau M. Okay, and now again, this part here also cancels here. So this is just M prime. Okay, so this proves that the map phi is surjective. Okay, so that's all I'm going to say. So technically, there's a little bit more that you need to check, right? So one thing that you do want is not only you want them to be isomorphic. So let me just make like a little remark here. This is something that if you want to be extra careful, I mean, you should do it to make everything correct, right? So we have this sequence here. This is the one thing we didn't really check. Okay, and so we had this map here, phi to M, and M prime prime 0. This was the identity. This was the identity here. Okay, and then we had this was J, and this was P. Okay, so one thing that you want to check is that these are that this commutes, right? So this was an isomorphism, and so so you just want to check that. And so this is so I guess what we should do is this is the inclusion, and this is the projection to M prime prime. Okay, so this one just kills the projection, kills the J prime component, and then this thing just sticks M as M prime comma 0. All right, so yeah, so we should actually be careful about checking the commutativity of the diagram. Right, because you don't just want it to be isomorphic to the direct sum. You want it to be the isomorphic to the direct sum with its two maps. Okay, that's kind of the important part. Okay, so yeah, so I'm going to leave this as an exercise. Right, so this is good exercise. Okay. All right, and so we just proved this top part. Okay, so all right, so in what else am I going to say? So the 3 implies 1. Oh, okay, sorry, I only did one part. So let me just say here. Okay, so 3 implies 1. So this is a similar exercise, right? So this is similar. and I put this on the worksheet. The problem sheet. Okay. All right. So yeah, I forgot about that part. Yeah. So all right. So are there any questions on this? So again, what was the statement? The statement was that that these notions of splitting are all the same, and they're being left split and being right split is the same thing as the sequence being the standard splitting, right? With the inclusion in the projection. Okay, so
what was S actually? Can I ask that? The S and C. What was the S again? From M prime to M. I think you defined it in the area, the middle map.
Can you say what? Can you ask your question again?
What was the S in that diagram? The very last diagram, you had an S going down.
This thing here. That's an isomorphism sign.
Oh, the S. Oh, okay. Well, I'll just.
This thing here. Oh, sorry.
Yeah, exactly.
Yeah. So
I forgot where that.
Sorry. So this thing here is an isomorphism sign. This is a tilde.
Oh, right. Okay. Okay.
Fism sign. Yeah.
Because that's question. What we just proved, that they're isomorphic.
Yeah. We just proved that this is an isomorphism. Yeah. Yeah. Sometimes people put these. So sometimes people put like a little like this next to the arrow if you want to show that it's an isomorphism sometimes. And some people do this. That's what I do. Okay. Good question. Any other questions? So it looks like I am not going to quite be able to show that that it's a direct summand, but the idea, of course, is that you're going to want to use a splitting, right? So yeah, okay. So it'll be very quick. I'll do this at the beginning of class next time. So, but yeah, the idea to show that every projective module, let's say finitely generated projective module, is a direct summand of a free module is, well, you're going to use this like lifting property to lift the identity map, and then you're going to use that to get a splitting, right? And so that's going to make it a direct summand. And I'll do that on Monday. So I'm going to go now to this memorial thing for Ray Hubler, who died last year. So thanks for listening.